Hi everyone. Good morning and good afternoon. So myself, Srihari, Godleti. I am currently working as a tech lead with Roku, a streaming company, which everybody is familiar, most of the people. And today I'm going to talk about how how to handle a data skew in a production ML pipelines and what are the challenges that we have uncovered, encountered, and then how we mitigated those issues technically and in a step by step process. So I try to cover as much as I can in these next 25 to 30 minutes. And so let's get started. As I mentioned, Rook is a streaming company. And in the streaming business, like we process billions of watch events and ad impressions every single day. And every replay, pause, or recommendation, impression, and ad click feeds into Spark pipelines powering like personalized models, embedded generation, and also ad ranking systems. So these are the different machine learning pipelines we run to understand the user's behavior while watching these shows or any television programs. On paper, like everything looks scalable, distributed computing, and partitioned at the storage level, auto scaling clusters, but can solve any many problems. But again, like in reality, what we have observed is jobs that normally runs in 40 minutes or less than an hour, suddenly it started taking like nearly 3 hours. And without any code change, any infra changes, we started seeing such a long running jobs. And when we investigated that why these jobs are taking a lot of time, and it's a case with the many other teams and whoever is using a Spark for their ETL compute and all that, we saw extreme task duration variance. That's because we encountered a silent performance bottleneck that's called a data skew. Today, I'm going to walk you through the skew manifestation in the manifest in the real ML pipelines and how systematically we can mitigate those kind of risks. Let's jump in. So the first question, why everybody have a question in the mind, like why these ML models are trying slowly? Earlier they were running good. So the ML pipelines are performance bottleneck is like ML plugged by the hidden performance killer that turns these minutes into hours, and training jobs extend indefinitely and model deployments get delayed. And so in turn, what we have seen is that our cloud costs burn through the budgets. So then who is the culprit here? Again, when we investigate, we saw data skew. So it's not just about the bad code, it's about like uneven data distribution or any spike in the events or watch events. That basically distribution across these partitions silently sabotaging your pipeline efficiency. So when we click when we click down into more technicality of this problem, and we see in the Spark stage, when the Spark has different stages, the if you know about the Spark process, and so a stage only completes when the slowest task finishes. In on the in the retraining jobs, we have observed that 95% of the tasks is completed like quickly within seconds, minutes, but one executor ran significantly longer and processing nearly more than 10x of more shuffle data than any other executor in that stage. And shuffle spills has been increased, and garbage collection pauses and CPU utilization is 100%, and cluster dropped because of the other executors who are cluster users is dropped and executors were idle. And this is a significant effect of a data skew problem, even though most partitions finish quickly, but entire job waits for one single partition. So let's look at what is this data skew in general. So a data skew in a simple words, what I call it as like the unbalanced workload problem. So your executors taking uneven data to process, uneven partitions to process. But what is the expectation in the ideal world is like we want to distribute this data evenly, spread across all the executors, all workers processing similar data volumes, and parallel processing, because the Spark itself is a distributed parallel processing ETL engine. and we want its full processing at a full efficiency and predictable completion times given the scale of the data. But in reality, with the skew problem, some executors process gigabytes while the other handle megabytes. The entire job waits for one particular or like the slowest executor, and the job times like take like very much longer, and the downstream, it has an impact of the downstream jobs, and it kills the entire the pipeline processing performance. And the resources is like these executors sit idle until the other worker completes his job. So when you talk about like the more deep dive into what is happening is like a Spark uses like hash partitioning during these shuffle operations, and data is distributed based on these hash num partitions. But the real world behavior follows the power law distribution. That means, for an example, as this is a streaming company, one user watches like a little program, so the other user watches a lot of programs and clicks on n different things while he's watching the program. And for the use case, like one user has two interactions, another user has like say 150 interactions. And when we group this data based on the user's behavior, and the heavy user dominates one partition, that partition spills to disk, and it overall increases the shuffle read time and causes the prolonged task runtime. And in this case, the parallelism breaks because of the workload is uneven. So how this is going to impact the production pipelines? The impact of the production pipelines I can categorize into two different categories. One is a technical performance impact. The other one is the bigger business impact. So when I talk about the technical performance impact is the feature engineering bottleneck. So you slow down on a features engineering just because your jobs are running and you need to handle these issues and extended model training times, and we want this job to be completed in 30 minutes but it's taking 3 to 4 hours. It's a bigger problem there. And delayed experimental cycles and model freshness, most importantly, as in case of the recommendation systems, and we want to process the data within fraction of seconds. And the business impact that I can see because of these technical difficulties and technical performance issues is a higher cloud infrastructure cost, just because like your resources is just idle and you are wasting money on them. And then slower time to market for models and reduced data science productivity. Of course, the ML models running longer than they used to, and we need to compromise on these SLAs and all that. So, so basically, skew, when we talk about the data skew, is it's not only increases the shuffle read size and specific tasks, it also have executor imbalances and also a lot of technicality in terms of like long garbage collection cycles. Most importantly, in recommendation systems, as I mentioned, as a business impact, the delayed retraining reduces personalized freshness, meaning so basically, you want to recommend as and when the user coming in and watching a program, and you want to recommend him like a similar kind of a content, and then thus that freshness and personalization is something it reduces. And in the ad ranking systems, like sometimes we have seen a 20% inefficiency just because of this data skew problem. When we talk about the business impact for this issue is like we can translate into millions annually in a compute cost just for the scale of 20% inefficiency. And so how like when we categorize these problems in the machine learning pipelines, how we can classify these problems. So one is there are different pipelines, ML pipelines, and that we are running currently. We have recommendation systems and we have classification models that we run, and also the computer vision pipelines that we run. So in general, in recommendation systems, a small number of power users or a viral content, for example, Super Bowl last week is like so many people watches and a lot of interactions, which can overload those specific partitions. In classification models, majority of those classes dominate the data set, creating imbalance and uneven executor workloads. Similarly, in computer vision, skews shows up both up in uneven class distribution, variable image processing times. This leads to the computational imbalance. And the key takeaway with this is the skew is not an accident, it is a natural outcome of real world events or data patterns that we are seeing, if not handled properly, this is going to cost a lot of millions of dollars for the companies, and at the scale of billions and billions of records we process for these recommendation systems and these classification models. So let's deep dive into what are the like different root causes this could the data skew should have. The first root cause I can think of is the natural imbalance, as I mentioned. This could be because of the bigger events like Super Bowl, and where we get a lot of traffic into the system. And training data naturally reflects these real world patterns where user behavior follows the power law distribution. So that means like the customers can concentrate geographically, and seasonal patterns create temporal imbalance. Like any event or Formula One or Super Bowl, any event can create that imbalance. So in that case, the most ML training data reflects these power law distributions, where a small number of users, products, and regions generate the majority of activity. This creates a skewed source data from the start, such as popular products, and like we have this ads category and highly active users dominating these data sets. When the partition data on these hotkeys, certain partitions become overloaded when while the others remain underutilized. So the problem often like propagates downstream into feature stores and model training pipelines, amplifying the performance bottlenecks. So this is one of the biggest problems that we have seen. And the key takeaway is that skew is not a system bug. It originates from it's from the real world behavior patterns and must be anticipated in these pipelines design. So the other root cause that I see most commonly for this data skew problem is the join keys and aggregation of these data on these join keys. So basically, like in this one, the join and aggregation operations during this feature engineering, when we join user features with behavioral data, certain popular or highly active user IDs can dominate the data set, creating these hard partitions and uneven workloads. This is a known as a join key skew. Similarly, aggregation operations like group by or reduce by key can suffer when a small number of keys contain disproportionately large volumes of the data. And temporary aggregation, such as daily, weekly summaries that we do, and often amplify this effect because of the activity levels can vary significantly across time. The key takeaway is that even the raw data looks manageable, but joins and aggregations can concentrate data in unexpected ways and create serious performance bottlenecks, all because of this data skew problem if we are not handled rightly. Another one that I can see is a computational skew, which means the text vector, in case of these machine learning models, text to vectorization, feature engineering, embedding generation is a deep learning vary in computation cost based on the input characteristics and model complexity. So even so, as we talked earlier, like even though we feel the data is right, and when we actually join this data, we have seen imbalances in terms of these partitions, and these joins is taking longer, much longer. So even in this case, like even the data is evenly distributed across the partitions, and workload imbalances can still occur, and NLP models handle variable length documents, and longer sequences require significantly more compute time. In feature engineering and complex transformations on these high cardinality categorical data create uneven processing loads. So this is like one of the, and we have seen these very frequently, which silently creates these performance bottlenecks in these distributed system. So as we have seen so far, what is the data skew, and what are those different root causes that we see the way data skew can reside and hide. So now we talk about more about how we can basically like mitigate these problems, data skew problems, in a step by step. The number one solution I can think of is repartitioning. So this is the concept like where instead of we give the system to distribute the data, we explicitly redistribute the data across the cluster by specifying the partition count and the column as I given in the code snippet. In this one, based on the user ID and given the repartitioning count is like 100, I want the Spark to redistribute the data across the executors. This forces Spark to rebalance the workload through hash partitioning. And this is mostly best for moderately skewed data sets and multi-stage ML pipelines and future engineering workflows, training data reprocessing. So this is most importantly, it is one of the best technique that we can use when we have a moderately less skewed data. The key takeaway is that repartition gives us the control over the data distribution and the better workload balance before expensive transformations like joins and aggregations. Let's move on to the next slide. The repartitioning. So when and how to apply. So the optimal setting for this one is the partition count 2 to 3x total core counts, where it all depends on which how big is your cluster, how many cores that you are working with, and the partition size is ideally 100 to 200 MB is our sweet spot in terms of the partitioning size count and balance parallelism with the overhead. So when we talk about the limitations and introduces a shuffle operation, so as you are redistributing the data, hash partitioning does not change the key frequency, ineffective for the extreme skew scenarios. Like when you have a large data, large skew for one particular region or something, then you need to think about other techniques to redistribute the data. So the performance gains, like moderate performance gain and most effective in future pipeline stages and all that. In our case, we observed with the redistribution, repartitioning strategy, and we have 30% improvement in our pre-processing stages. However, repartitioning does not change key frequency. Extreme hard keys still remain dominant, as I mentioned in the slide, and optimal partition size is like 100 to 200 MB. Moving on, the second solution that we that's most recommended and most popular is a key salting. Meaning like, so you identify the hard key, which is improper distribution. You add a salt to it, you add a random number or some number and spread those partitions. So in that example, I just added like a random of some random number into multiply by 10 with the user ID and then redistributing the data. So this gives, so when certain keys such as high active user IDs dominate the data set, repartitioning alone may not be enough. Key sorting works by adding a small random value, as I mentioned in the slide, effectively splitting the single hard key into multiple smaller keys. This spreads the workload across multiple partitions, breaks up hotspots. So the key takeaway is that salting allows us proactively distribute the extreme skew when specific keys are responsible for overwhelming the cluster with a large partition of data and one executive taking that entire load. So what are the best scenarios like when we can use like low salt? So there are like 2 to 4 keys like that, and we need to do 34. So resolve for extreme skew. So when a single dominant value, so as I mentioned, like there is a dominant key, hotkeys will be there. And so what we do, we append the random salt keys to heavy user IDs before aggregation. Large partition reduces from 8 gig, like in our case, like 8 gig to 600 MB, or training runtime reduced like nearly 50% in some cases. And salting requires an additional aggregation stage, but stabilizes the workloads significantly. And the last one here I have is the broadcast join. This is also very significant in terms of improving the Spark jobs performance and skew when we have a skewed data. So it's always ideal to send the smallest table into the memory. So send small table to all executor to join, and it increases the join performance, and also this eliminates the shuffle. That is a big thing of your large data set entirely. As I mentioned in the code snippet here, we just need to use the broadcast. Spark will understand this is the small table, this is the table that need to be sent to memory for all the executors, and it will broadcast the data. So basically, essentially, what we are trying to do is like we try to avoid redistributing the large data sets across the cluster. This drastically reduces the network overhead. Broadcast joins are effective in future engineering pipelines, whereas large behavioral data is joined with a relatively small dimension or lookup data table. The key takeaway is that in this one, instead of moving massive data across the cluster, we move the smaller table once and process the join more effectively and efficiently. This way, our model performance, like the pipeline performance, is significantly improved. So here are some guidelines and best practices that we can use. Keep the broadcast table under 10 MB. There's a typical limit. Use a maximum of 20-25% of executor memory to avoid GC garbage pressure during training and significant data size disparity between tables. So that means like when you're joining a 100 gig table with a 1 GB of data set, so that's when the broadcast will be very helpful and handy, and then we can send this small table into memory for a more efficient join. And performance impact, it eliminates the, as I mentioned, it eliminates a lot of network traffic and network shuffle and scales with the table size difference and critical for maintaining model freshness in production systems. So in this case, this, as I mentioned before, this avoids a shuffle of large data sets and one enrichment stage drop, like in our case, like 90 minutes to almost 10, close to 10 minutes, ensures the broadcast join size remains under 20-25% executed memory to prevent these GC overhead issue. So overall, the key takeaway, so we understand what is the data skew and how it is going to impact our production ML skews and what are the root causes and what are those like mitigations that we can do in terms of avoid this data skew and handle it. We can't avoid the data skew, we can handle the data skew in a right way. And so basically, like as I said, use the repartitioning when the data skew is like moderate skew, or if you have a larger skew. In most of the cases, we have used mostly the salting in terms of skew data and broadcast joints, which help us significantly optimizes selective targeting specific bottlenecks rather than over engineering the entire pipeline. Finally, so I would say when implemented correctly, these techniques lead to faster model training. So it saves a lot of cost and time, and also freshness of the keep the freshness of the data and better resource utilization, lower infrastructure costs, and also it will help to do a quicker development cycles. So with that, we are also currently working on how we can leverage AI in terms of identifying these gaps in a prehand and help us suggest like when there is a data skew that's going to happen, we want to scan through these data sets and help suggest these are the hotkeys, or this is where the data is being distributed heavily. So then so that like with the help of AI, we are experimenting with models trained on historical Spark metrics to predict the data skew risk before stage execution. These models could recommend partition counts, as I said, and salting factors and broadcast strategies. Dynamically, this represents a shift towards a self-optimizing distributed ML pipelines. That's what we are planning to achieve. With that, thank you everyone, and hope you like the content. If you want me to really want to connect on LinkedIn, you can type Godleti, and I'm happy to talk more. Thank you.